does this work? There we go. So I'm going to talk about chemical interfaces as well, and a little bit of spectroscopy. I'm going to talk about slip flow. But first, I want to congratulate our guest of honor, Jerry Richmond. And I first met Jerry through spectroscopy of surfaces, which I did a lot of in the past. And now I'm doing more chromatography, which is a big application of what I'm going to talk about today. But I mainly know Jerry now through Coach. And so what I did, unlike Bruce, was I pulled off a bunch of things from Jerry's Facebook page, which she's not embarrassed by. And so these are things she wanted to have in public. Yeah, I know. But Jerry amazes me. You know, not only is she a great spectroscopist, you know, a huge number of very prestigious awards, including this one, and member of the National Academy of Sciences, but also the mother of two beautiful, really handsome guys. Now that they're grown up, wow. And also the head of Coach, which has mentored, you know, many thousands of women. What is it, up to 8,000 now women? 10,000. It's changing fast. And Jerry travels all around the world very frequently. And so these are pictures from various places. And I'm sure this thing works. See, I stopped doing laser spectroscopy. So you know, Thailand. I think both of these are from Kenya, where I had a chance to visit as well, and Morocco, where I also was. But Jerry just travels so amazingly much, never gets jet lag or anything. And so I did a rough calculation of Jerry's average velocity since she travels so much, and it's about 20 miles an hour, and that might be an underestimate. So anyway, congratulations again, Jerry. There's also a Delaware connection in this symposium. So we had Bruce talk, who's now at University of Delaware, and Sharon Neal talk. And this is an SEM image that I took at the University of Delaware when I was on the faculty there. So here's my Delaware connection slide. And this was our first image of a silica colloidal crystal. And so I had seen images in the physics literature back then. So this is, I'm not sure if the date is still on here, but it's yeah, there it is, June 25th, 2002, which was several days before my NIH proposal was due. And this went into my NIH proposal. And I got excited about these. These were being used as photonic materials in the physics community. And so that means that they would exclude a narrow bandwidth of light. And it's by diffraction. So these things act like three-dimensional diffraction gratings. And I looked at pictures of these and I thought, God, that's the most beautiful chromatographic material I've ever seen. And you can also potentially use it for electrophoresis because you have these pretty uniform pores that you know, these are 200 nanometer particles, and so the pore diameter is on the order of what you have in polyacrylamide electrophoresis gels. And so we just have to figure out how to start making these. And so this was the first one. Well, we had made many, but we didn't have an SEM. So this was right after Delaware took delivery on a field emission SEM and proudly got this picture. And so I want to tell you about the work that we've done since then on these, you know, getting better and better and better at making these things and finding very interesting properties of these things. And so, as I said, my initial interest was in separations, and so this is my big separation slide, all of the things that cause broadening. So this H is a measure of zone broadening. It's the variance normalized for the length. And there's all these different terms. And just to cluster these together, the top row are all bad things caused by big particle size. And so the smallest particle size that's used in commercial chromatographic instruments is about 1.7 microns. And people who empty these out and measure them say it's really more like 1.9 microns. And so these are really tiny particles we're looking at. And most of what I do now is use 500 nanometer particles. So about a factor of 4 smaller, actually a little under 500 nanometers. So almost exactly a factor of 4 smaller. And so it should make these terms a lot smaller. And so I was able to convince NIH to make a gamble on this, and the gamble seems to be paying off. And then even things like diffusion, which I'm going to talk about today, could potentially benefit from this as well. And so that was my initial motivation. And it's getting late in the day, so I'm going to also show you some pretty pictures. This was our very first silica colloidal crystal we ever made. So this was with my old Kodak camera, which was the first digital camera, and the dime is behind it. I remember one time I showed this at a meeting, and somebody said, "That's really pretty. Why'd you put a dime on top of it?" And so the dime is behind it to show that it's transparent, so that you could easily detect inside of these things. And then the trace here is effectively absorbent, so Beer's law. The transmission is reduced when you're at the band gap, and so you get this peak, and the peak is related to the refractive index difference between the air and the material, and so that's why it's a photonic material. And if you make it really, really thin, you start losing the effect of this three-dimensional diffraction grading, and it shifts as well. But they're relatively transparent, except for the place where you have the band gap, and that's what gives it the blue color. So it's very pure silica that we use, but it gets a color because of this Bragg diffraction. And this is my Sandy Asher slide, actually, who's seated right here next to me. So I first heard about colloidal crystals from Sandy Asher. And Sandy's done a lot of beautiful work using polymer beads instead of silica beads. And so this is one, we're now getting better and better at this. This is one we made in our lab with silica. What Sandy does is he uses polymer spheres that are charged, and they are fluid in solution, and so they keep this distance because of electrostatic repulsion, as opposed to ours, which have this hard sphere repulsion. And so I always make the distinction between Sandy Asher colloidal crystals. So you're famous in the chromatography world, as well as the spectroscopy world. And so this is a picture I showed Sandy last year at Pittcon, where my student Robert Birdsall took a Pasteur pipette. So this is a big blow up of it. And he let it sit for a month with a concentrated slurry of silica particles in them. And silica at neutral pH has a charged surface. And so when these get really concentrated, they form a Sandy Asher type of colloidal crystal at the top, which has bigger spacing, so you have red diffraction. And then as they drop and form the solid, now they're closer together and you get this green diffraction. And there's different crystal faces. You can see these things. The 111 and the 100 face have different spacings, and so that's why you get these different colors. And this is actually what opals are made of, geologic gem quality opals. They're made out of silica particles, and so you get these beautiful colors from these different facets. And so my students are making these in all sorts of media, and we've done a lot of work with packing capillaries with these. My student Bing-Chuan Wei packed this 75 micron ID capillary, so this is the plastic cladding around the capillary. And we took a color photo of it in a zoom microscope, really tiny domains, and then we have a scanning electron microscope right next to the optical microscope, and so we moved it over without changing the orientation and took an SEM of this little region here, so that use a small enough region so that you can still see the curvature a little bit, but you can make out the silica particles, and so you can see these little tiny domains, and so that's what we use in chromatography. So we don't need to have enormously large domains. Although my students do like to play with this and sometimes make really big domains. And so this is one that really looks like an opal inside of a capillary. And they found on the web a gem quality opal that apparently has the same particle sizes, so you see all the same colors. And when I show this, a lot of people ask me, well, can't you scale this up and make beautiful gem quality opals? And I always respond, have you priced chromatography columns lately? They're almost like they're almost as much as gem quality opals now. So anyway, what we're doing now is doing separations inside capillaries, doing both electrophoresis and chromatography. So when we made these, one of the first questions we had was can you get molecules into these things? And so we published a lot of papers showing that you can get molecules in these things, but only to a point. So, oops, this thing has a mind of its own, as you found. Yeah, and so one of the papers we published recently, this is in Journal of Physical Chemistry, is looking at what proteins can get into this thing. And so this is a big table. I'm going to try to guide you to what you really need to look at. So we talk about porosity. How much free volume do these have? And so if a molecule, to get a molecule into this, you have to have you have to have some free volume, or if it's a solid, the molecule won't go in. And the pore size of that has to be big enough for the molecule to get in. And we want to use this for protein separation, and so proteins can get pretty big. So this is a small molecule, fluorescein, larger cytochrome C, larger yet BSA, and then finally the thing that is very important technologically to separate today is our monoclonal antibodies, which are the biggest of all. And we did a fluorescence experiment, fluorescence recovery after photobleaching, where we looked at fluorescein, and then each of these was tagged with fluorescein so we could measure the diffusion coefficient. And we made the assumption, just based on the polymer literature, that the porosity would be the ratio of the diffusion coefficient that you measure in the material to the diffusion coefficient that you would measure outside the material. So we measure each of those with FRAP the same way, same graduate student and everything. And so that's how we get the porosity. And so when the particles are really tiny, they're very well behaved. You get a porosity that matches what is predicted for a face-centered cubic crystal. And so around 200 or less, between 100 and 200, you just get really, really nice behavior. Pretty darn good behavior, close to 500 nanometers, which is mostly what we're running with. And then as you get to bigger particles, just other, the forces, the van der Waals forces between the particles are different compared to just RT, and so they just don't form quite as spontaneously. And so now you start getting if it were completely random, the porosity would be 0.4. And so we measure that with this equation, and then we look at how much of this porosity is available to the protein. And so, if it's fluorescein and it's a big particle size, almost all of the free volume is available to fluorescein, and it is all the way until you start really getting down onto the molecular scale. So the particle looks big, but the spaces between the particles are really tiny. So even fluorescein can't reach all of the free volume. The monoclonal antibodies don't want to go into anything smaller than 470. They'll go in, you just have to wait a long time. And my student ran out of patience and says, I'm not waiting for this to go in anymore. And so to do anything practical with monoclonal antibodies, we use 470. Someday when we start looking at small molecules, we'll use even smaller particles. So we're talking about really little dimensions here. And I said that we made the assumption that this ratio of diffusion coefficients was the porosity. We independently measured the porosity. And then there's also, this is actually from the 19th century, James Maxwell said that the porosity should be measured by the ratio of the current without the material, or the current in the material to the current without the material. And what we found was all of these things agreed. So as far as I know, we're the first group that actually measured both diffusion coefficient ratio and current ratio and showed that they agreed. And it was interesting to us because in the chromatographic literature, they would tell you, no, there's a factor of roughly 2 here, and in the chemical engineering literature. But in the polymer literature, this is what they use. And so we wondered, what are you actually supposed to use when you talk about obstructed diffusion? And so the obstructed diffusion looks to us like it's just simply related to this fractional free volume. So all looks good, but sometimes you run into things that are really funny. So a few years ago, we published a paper using electrochromatography, and in the supporting information, we showed, and we just mentioned in the paper, you could actually flow through these. And we didn't know whether you could really flow through these with any reasonable efficiency or not, but we found that you could, and it was a collaborator of ours who had a really high pressure pump. We shipped her these capillaries, she measured them, and we got these really nice flows. And a very observant reader got more interest. He worked for a chromatography company. He was more interested in the flow than he was in the rest of the paper. And he did this calculation based on something called the Cosini-Karman equation. And this is what the flow versus pressure ought to look like. And so we were getting more flow than expected. And so he demanded an explanation for this. And of course, we didn't have one. I don't know why we get more flow. And so we had sent this group 5 capillaries, and one of them broke, but the other 4, it was 3, I can't remember, all agreed. And so we started making our own measurements, and we found that these things always gave more flow than expected. And so we wrote a response to the comment. To make a long story short, it basically said, we don't know, but it's right. So we had more flow than expected. And so meanwhile, we started using these things in chromatography, and then we got another surprise that disobeyed theory. And so we could have been arrested by theoreticians back then, I suppose, breaking all these rules. But we started making some measurements using pressure-driven flow, since we had this nice flow. And this is, in the chromatography world, this is a very shocking sort of thing. So this is bovine serum albumin, which usually gives really broad peaks, emerging near the end of a 2-centimeter long capillary. One's labeled much more than the other, so that changes the retention time. So we have 2 different peaks coming out, and they're cleanly resolved. And this is a capillary 75 microns wide, which means that the zone widths are microscopic. And so you don't usually use a microscope for your chromatographic detector. And so pressure-driven flow, extremely narrow peaks. And the plate height for a protein is normally about 8 microns, the best you can do. And these things came out to be almost 3 orders of magnitude better. And there's something called the reduced plate height that a lot of people use, which is, okay, you're going to improve the plate height, as I said earlier, with smaller particle diameter, but it's predictable how well you'll do. So if you divide your plate height by the particle diameter, back then it was thought this could never be less than unity, and we saw 0.03. And what that meant was that we couldn't possibly publish this work. It was just way too far from what was possible. And so reviewers all sent it back. You clearly made some terrible mistake. You either miscalculated. So some people thought that the column was only this long. And so we labeled things much better so that you could see that it was 2 centimeters long. People thought people thought of all sorts of things we were doing wrong. But we measured many other proteins, and all of these plate heights were much smaller than unity, very, very tiny. And so what we eventually realized was that, and theory has caught up, incidentally, by the way, so as theory often does when you do reproducible experiments. But what we did was we went back and looked at all of the things that cause broadening, and we knew we were getting rid of this term. We had proven that it was less than 5 nanometers. We did that with electrochromatography. We didn't have any porosity, so that we're using non-porous particles. So it had to be this term, this Poiseuille flow profile term. And this gives broadening because a molecule that's in the middle of the stream has a higher velocity than a molecule near the side. Now, some of this is averaged by diffusion, which is why diffusion is in the denominator here, but it never completely averages, so there's always some residual amount of broadening from that. And so this was the suspect term that was used in all of the theory. And so thinking about this Poiseuille flow profile, what all of us learn when we read chromatography books is that it's got a parabolic shape and it goes to 0 at the wall. Just like when you're canoeing down a stream, the velocity is fastest in the middle, slowest at the side. So if you want to eat your lunch, you pull off to the side and have your sandwich, or take your photo of the bald eagle or whatever, then go back in the middle. So I have a drawing here to describe this. This is actually an SEM image of a planar silica colloidal crystal we made, and the top of the silica colloidal crystal. And so if you So we're not using capillaries. That's really the message here. So we're picturing the flow region as being in between these particles, so I blew this up. And so when I talk about a wall, I'm talking about the wall of a particle. And when I'm talking about the Poiseuille flow profile, you would make a cross-section like so, and you'd be looking at just that one cross-section of this. So the reason why the velocity would go to 0 at the wall is because when the molecules go to the wall, they'll interact. If you've got a silica wall, which has hydroxyl groups and has a layer of stationary water on it, a molecule can bump into this, have a hydrogen bonding interaction, which makes it stop for some period, some short period of time, and then it will leave again. So molecules reaching the wall will stop if they have some attractive interaction with the surface. So when this was first described by Navier in 1823, he had a choice between having molecules stop at the wall or having the fluid stop at the wall, because they didn't really necessarily agree that there were molecules back then. But the fluid would go to 0 at the wall, or the fluid wouldn't go to 0 at the wall. And so what he did was he solved both cases. And everybody ignores the second case where the fluid doesn't go to 0. And so the fluid velocity doesn't go to 0. So why would the fluid velocity not go to 0? Well, in the chromatography that we do, we have a hydrocarbon monolayer. And so the water does not interact strongly with the hydrocarbon monolayer. And so why should the water stop? There's a force being applied from above here by the fluid, and so it will keep going, so there should be some non-zero velocity. And so Navier called that slip flow. And so that was actually, I think in his mind, the default. There was slip flow, and then there was no slip flow if it stopped at the wall. So there were equations for both of these. And so people describe this, and Navier did as well, by some putative slip length, which is a mathematical construct, where the flow profile doesn't go to 0, but you just continue the parabola, and then where it intersects is the slip distance. And so we wanted to know if is that the explanation for why we're doing so well in the chromatography. And so my student Ben Rogers went into the lab, and he measured flow rate for a few different liquids that are compatible with a chromatograph. So water, 50-50 acetonitrile water, acetonitrile, and then he made a toluene reservoir. You can't run toluene through your HPLC, so don't do this at home. He made a reservoir of toluene in line so that it didn't go through any of the tubing. And the flow rate's normalized here for viscosity. So if you normalize for viscosity, if nothing funny's happening at the interface, all of these should line up, because that's the only thing that affects the flow rate. And what you can see is that water has the highest flow rate when you normalize for viscosity. Toluene has the lowest. Toluene is the one that would interact the most at the hydrocarbon surface, and this dotted line is the theoretical prediction for the Poiseuille flow. And so toluene matches Poiseuille flow very well. The rest of these lines are linear fits in order for us to get the slope and determine the flow enhancement. And so this is really good evidence. This is very convincing evidence that we have slip flow, and that's the explanation for the better chromatographic performance. And so with this, we were able to get the paper published as a JACS communication, and then a theoretician got interested in this and improved the theory as well. And so now the results agree pretty nicely with theory, accounting for the slip flow as well as accounting for the fact that the protein doesn't reach all of the interstitial volume, and so it stays a little bit more in the center of the flow stream, and that explains the results that we're getting. So we played around with this a little bit to help illustrate slip flow, especially to the chromatographic community that wasn't familiar with it. And the reason they weren't familiar with it is it's a nanofluidic phenomenon, and so I want to talk about that a little bit. Why is it nanoscale and not microscale? And so if I take 3.6 micron particles, which would be very familiar to chromatographers, and plot the normalized flow rate for water and toluene, they line up really well. You know, the instrument always gives a little bit of an offset, but, you know, these overlap within error. So flow versus pressure, water and toluene line up really well with 3.6 micron particles. If you go to really tiny particles, 125 nanometers, this is what you get. So now, again, normalized for viscosity, that's water, that's toluene. And the dotted line, again, is the Hagen-Poiseuille flow, so predicted theoretically. Again, it lines up really, really nicely with this. So toluene has no slip flow, and water has huge slip flow. The slopes differ by a factor of 20. And so if you're able to go down to 125 nanometer particles, you can get this 20-fold enhanced flow rate, which is really amazing. It actually makes it feasible to start thinking about using ridiculously small particles in HPLC. The reason why people had stopped at about 1.7 was because the calculations tell you that the resistance to flow is prohibitive, and you're not going to do any better when you go slower. But now this tells us no, you can go to smaller particles and still get good flow rates. And in addition, there's something else going on that some of you might have thought about already as I'm talking here. When you have a small porosity, a small interstitial volume, the velocity through the material is higher. So you actually need to work at a slower volume flow rate with materials that have lower porosity. And so you actually gain two ways. One is with the slip flow, and then the other is with the smaller optimal volume flow rate. And so it makes all of these things feasible. And so we're starting to use HPLC with these really tiny little particles. I wanted to explain why it's a nanoscale phenomenon. So I'm hoping that this helps explain it. So if I say that the slip distance is fixed, and this is a property of the interface. So property of, you know, in this case, let's think about the water hydrocarbon interface. And so the slip length is a function of that. I wish I could write out what function it was, but nobody has really come up with that yet. So nobody actually has written a functionality related to contact angle or something like that, but it's a property of the interface. And so if I fix that and just change the radius, well, now you can see that the wall velocity goes up. And so it's a little bit of a kind of a fake way of saying this, because I say, well, here's the equation. I'm really telling you the equation says this. But probably the way that I think about it is that you've got this flow stream in the middle that's going at a high velocity, and the sheet, you know, this is just laminar flow, right? The sheet next to that is in communication with this, and so it's going to be going at a similar flow rate, and so on. And you don't go very much distance before you get the wall. You get to the wall, and so this wall velocity is in better communication with the center than this wall velocity that's way over there. And then it doesn't have a strong interaction along the wall to impede it, and so it's not going to get to zero fast when it doesn't have much distance to go through. So that's the way I like to think about it. So it's a nanoscale phenomenon. And here are some data to help illustrate that. So my student Ben Rogers, who was very energetic, took a whole bunch of different particle sizes from this 1300 that I showed you earlier all the way down to, this is something like 122 plus or minus 2, so we sometimes call it 120, sometimes 125. The error bars are from 3 different capillaries. So he made 3 capillaries for each of these and then measured multiple flow rates. So multiple pressure versus flow curves had about 5 points. So many points went on to this. And so this is a plot of flow enhancement versus the hydraulic radius between the particles. And so this is something that just comes from old fluid mechanics. If you take the particle size and you know the porosity, you can get the effective pore size in the medium. And then we use Navier's old equation from 1823 to and constant slip rate slip distance. And so we can fit this, and it fits very nicely. So this curve is actually a fit to this equation with a slip length of 63 plus or minus 3 nanometers from the 3 nanometer error coming from the regression. And so, so this illustrates that a packed bed obeys this equation that was derived for capillaries. That this is the most precision ever reported, as far as I know, on a slip length, and so it gives you an idea for planning what you expect the slip length to be. This is with a butyl hydrocarbon chain. We get more slip flow when we use longer chains. So, for example, with these 470 nanometer particles, for the C4 we get a factor of 5. For C18 we get a 10-fold flow rate enhancement. So, whopping flow rate enhancement allows you to start using reasonably long columns with half-micron particles using commercial pumps. And so that's pretty amazing. The 5-fold flow enhancement, if you were to just visualize what that is, I did this calculation. This has a 5-fold average volume flow rate. And so 0 wall velocity here if it were Hagen-Poiseuille. So this gives you an idea of what the wall velocity would look like relative to the maximum velocity if you have a 5-fold flow enhancement. And so what's driving this improvement in chromatography then, or at least part of it, is that now you have this narrower distribution of velocities. So here you have a huge distribution. It's all and then nothing on the side, and there's a lot of area on the periphery of a circle. And here, this gets a huge head start on the periphery of the circle, and so you've got a much narrower distribution of velocities. And so, even if none of this had happened, just going to a half-micron particle size would be advantageous in HPLC. But this makes it possible to use longer lengths, to use reasonable lengths. We can go up to 10-centimeter columns with this, which is more than what people typically would use for protein separations, certainly more than what they use for UHPLC. Plus, you get this additional bonus of a further improvement in the performance. And so what I want to do is I want to just mention one other thing. Okay, I'm almost done. And so these two theoreticians, chemical engineers in China, published a really nice paper talking about everything I've said in terms of the model is for capillaries, and they showed that you don't get quite as much of an enhancement in packed particles. So this is one of these three-dimensional pictures of the interstitial area inside of a colloidal crystal, and so what happens is at some point the flow has to hit a particle and slow down. So I put this color coding on here. And so if the velocity streams were all the same length, this would be all the same color. So Hagen-Poiseuille flow goes to 0 at the walls, doesn't go nearly to 0 at the walls for slip flow. And then you don't quite get as much as you hope to get out because of the velocity. It has to go to 0 when in those places in the crystal where the fluid is directly hitting the top of a particle. But it's still pretty darn good. And then applications, so we've published some papers using commercial instrumentation. We have to be concerned about Poiseuille flow through the tubing. If you look carefully at this, there's tubing all over the place. So after the column, we can't let it go through tubing. This is a picture we took in our lab of Poiseuille flow. So we did isoelectric focusing to get a really sharp peak. Apply a little bit of flow. It really is a parabola. You can tell that. And this, it just stretches out right away. And so you got to be really careful when you go into tubing. You want to go from a big diameter to a really tiny diameter so that it goes through there in no time at all. Shortest tubing that you can get by with in order to minimize this. This is a really neat result that we got. So compared with a reverse phase column, 1.7 micron particles. This is an Eli Lilly monoclonal antibody. Pure, so this is a sharp peak for the commercial column, sharp peak for ours. These are 3 replicates, that's why you see the different colors. So extremely reproducible. Half of a centimeter. This is a 5 centimeter length, half of a centimeter. And then Eli Lilly gave us this formula for how to coax this to make aggregates. And so you see the aggregate here, unresolved just as a shoulder. We have size exclusion data to give the mirror image of this, showing that it really did aggregate. And then in 1.25 centimeters, which is a ridiculously small distance, we get the monomer, the dimer, and the trimer resolved. And so now what we're doing is we're working on making the length longer and starting to put this into stainless steel columns so that people can collect fractions. And there's a huge story behind all of this, and I'm organizing a full-day symposium at the San Francisco ACS meeting on monoclonal antibodies with all kinds of biopharmaceutical companies contributing. And we've also done some nanospray work as well, and so these can be used in mass spectrometry, and just incredible resolution, and so my time is up, and so I thank the funding agencies, my graduate students, hardworking graduate students, some of whom are in the audience. I can see you back there smiling, and once again, congratulations, Jerry. Yeah. Dennis, yes. There's nobody there, right?
Just interested to think about how particles get in the way, but it's all about the particles. Makes me think about microfluidics. Are there any applications of better understanding of this non-zero wall velocity to maybe mixing and microfluidic chambers?
Yeah. It's actually, people in gas chromatography have to use slip corrections all the time because gases don't interact very strongly with walls. And so it's funny, there's been this bifurcation between gas and liquid chromatography. They all know about slip flow, and liquid chromatographers don't. Yeah, certainly it's something that could either help or perhaps get in the way in microfluidics if you had a slippery wall, in terms of trying to get things to mix. So, yeah, Sharon. Yeah. Okay, I multiplied it times 4 because Navier was a really smart guy, and that's what he said to multiply it by. But it wouldn't have hurt if he just lumped the two together, I suppose. So that's just the way. It doesn't really represent something physical. So it's defined as the ratio of the velocity to the shear rate. And so that's as physical as it gets. And so the velocity to the shear rate, so how fast is this stuff going relative to how hard I'm pushing it? And so that's related to the interactions in some way that hasn't been solved analytically yet. It's really hard to measure this stuff. So if in writing these papers, we went through the slip flow literature. The numbers for a water hydrocarbon interface vary from, for the slip lengths vary from less than 30 nanometers out to, microns. And so there's a lot of them in the hundreds. There's some of them in the 30s. They're just all over the place, because you have to get to these really small dimensions. So you can't do that with capillaries. People have tried using turf to look at velocities just right at the interface, laser Doppler velocimetry, all sorts of things. There's just no consensus. And so we're happy that we made something that reproducibly gives us the same slip length all the time, even though it's not an open, it's not a cylinder. At least we get something that has a known slip length. Yeah, there's a question behind you. Yep. There. Yeah, it does. And so this, yeah. Okay, yeah, right. So so what I did here, I kind of there's a lot of data on this. I went through this kind of fast. And so this is a plot. So let's look at the equation first. So this is the flow rate. So if I take Q over Q, Hagen-Poiseuille, I'm going to get my flow enhancement. So this is the ratio of the Q over QHP. And so then it's fitting to 1 + 4 slip length over the hydrodynamic radius. And so I need to plot this versus hydrodynamic radius. I get that from the particle size. Now, I could do as you were suggesting, which is just plot it versus particle size. The only reason we couldn't do that is because different particle sizes give us different porosities. We get the lowest porosity just for these two things on the end, and then the other ones tend to give us higher porosities. So I had to include that because that actually changes what the effective hydrodynamic radius is. No, it's not, because the same 63 goes through all of these points. Yeah. No, it shouldn't. It's not supposed to be dependent on so hydrodynamic radius is separate in this equation. So it's supposed to be a function of the interfacial interactions. So if I change the liquid from water to acetonitrile, I would get a different slip length. It would be shorter. Mm-hmm. Right.
Mary, how do you pack the columns? And are they random packed?
No, they're not random packed. So they all have porosities less than 0.4. So 0.4 is random packing.
Okay, so so you're saying that these are face-centered cubic packed structures?
They're pretty close to it, and so.
How did you make it that way?
Yeah, so how we made it that way was through quite a few years of sweat and swearing and all of that, until we finally figured out how to see a lot of people. Bing Chuan Wei was a person who really figured out how to do this, and he's sitting back there with a big grin on his face because the sweating, perhaps not swearing, maybe in Chinese, and I didn't know, but what we had was, and Bing showed this in one of his papers, is that you tend to get voids at the walls, and so the particles, they want to cluster together, and then you have these wall voids, which I think Jim Jorgensen published a paper showing, nobody had ever thought about this in HPLC columns before, but he showed you actually have these in HPLC columns. And so we sonicate, and that forces the particles to fill up the whole volume instead of, it beats some of the clustering that the particles are naturally trying to do while you pack.
Now if you're sonicating, then why do you go to a face-centered cubic structure instead of a random closed pair?
Yeah, so very good question. So why do we get a face-centered cubic structure? So when we designed the sonication, I was picturing in my head how diamonds are formed. So they're not random, right? So, beautiful crystalline structures. And so they're formed at high temperature and high pressure. And so I thought of the sonication as analogous to temperature, and then we have this high pressure pump pushing it against the frit. And so I thought we ought to get crystallization if we balance the magnitude of the pressure with the magnitude of the sonication. And so that's what we did, and it works nicely and fills up the whole volume of the capillary.
Okay, well, thanks. Very nice talk.
Thank you.